Okay, so we're going to do 2D vectors first. 2D means two-dimensional, right there. And we will get into 3D vectors right after. So I am going to do vectors today, and we're going to do vectors for like the first week and a half or so. But I do want to lay out in 25 words or less, maybe a little bit more than 25 words, what Calculus 3 is going to cover. Like, what's the semester going to entail? I bet you're interested in hearing that, aren't you? So here it is. Calculus 3 is going to be Calculus 1 all over again, but in 3 dimensions instead of 2 dimensions. Isn't that great? Yeah, that's what we're doing. And here's some even better news for you. Remember all those sequences and series that you did in Calculus 2? We're not going to do any of those in this class. Isn't that great? Now, that's not to say that you're not going to use those in another class. So if you're taking differential equations, they will be doing series in that class. And I've taught that class. It's a wonderful class. So that material that you did learn in Calculus 2 will be relevant. So don't completely forget it if you want to do well in differential equations. So in a nutshell, here are 2 things that you did in Calculus 1 that we're going to do in Calculus 3. The first thing is, if you recall in Calculus 1, if you were given, say, the graph of a function, say y equals f of x, one of the big things you did back in Calc 1 is they would pick a point, say right here, when x is, I'm just going to make something up, say some number c, and they would go, hey, what's the slope of the tangent line at that point? And in Calc 1, I hope you remember, oh yeah, we did that. And what was the slope of this tangent line? Does anybody remember how to get a slope of a tangent line to the graph of y equals f of x? If you don't, that's okay, but
Derivative?
yes, thank you. Yeah, the derivative. So the slope would be f prime of x, or in this case, f prime of c, because we want it right there when x is equal to c. So in Calculus 3, you're going to be doing a similar thing. Really? Yeah. We're going to be working in 3D. So you'll have 3 coordinate axes instead of just 2. And we're going to be looking at the graph of a surface instead of a curve. So you'll be having some surface. I'll just graph this is like a capping surface here. If you can imagine, this is 3D. And then we can pick a point. You can think of that as being a mountaintop, if that helps. I'll pick a point on the mountain, like right there. And let's say you're a skier and you're going to ski down the mountain. What's the slope right there? We're going to go over how to do that here in Calculus 3. Pretty cool, huh? The second thing that you learned in Calculus 1, just as a reminder, is, again, you'd have some graph of y equals f of x. And then do you guys remember that back in that day, when you took your Calc 1 class, they would ask you to find the area under the curve? Calculus 1. Does anybody remember how you would find the area under that curve?
By the integral.
Good. You'd integrate from what to what?
From a to b.
Good. And then what would you put here in the integrand?
Your equation, and then you end with dx or dy or something.
Yeah, in this case dx, because we've got on the x. Yeah, so your area was an integral. So what did you do in Calc 1 in a nutshell? You did derivatives and you did integrals, but you were working in 2 dimensions. Here in Calc 3, we're going to do derivatives in a different way, of course. And then instead of area, we would find the volume of this solid that would have the capping surface of this pink thing. So you're going to be looking at finding a volume, and it's going to involve a double integral or a triple integral. Don't worry about that right now. That's not for like 3 months away. And that's basically what Calculus 3 will be about, is doing Calculus 1 all over again in 3 dimensions. Exciting stuff. So we're going to look at vectors in the plane. So this word plane is not an airplane. So anytime you hear the word plane from now on in this Calculus 3 course, think 2 dimensions. And you'll see that in the textbook. You'll see it on some of the homeworks and quiz problems. They'll say, oh, check out these vectors in the plane. And immediately I want you to think, ooh, 2 dimensions. 2 dimensions. Okay, now let's get some definitions out of the way, and then we'll have some fun and play with vectors. Okay, so introductory definitions. Scalar quantities. What the heck is a scalar quantity? You may have heard the word scalar before. Scalar quantities are physical quantities that can be characterized by a, and write this down, single real number. That's right, just a single real number. That's called a scalar. What's some examples of scalars? Well, the length of something is a scalar. Like I'm on a table right here. It's a card table. It's kind of cheesy. But like, what would be the length of one of the sides of this table? I don't know, probably looks to me like it's 3 feet. The 3 is a scalar. It's a pure number. Area is a scalar example. Volume would be another scalar example. And there are many, many more. Vector quantities. Vector quantities are quantities that involve both. So that's going to be 2 things here. So write these down. Number 1, a direction. And number 2, magnitude. Now, magnitude is kind of a weird word. It's a fancy word for length, but it may not always mean length if you're working with vectors that are in 4 dimensions or 5 dimensions or 20 dimensions. Now, in this course, we're going to limit ourselves to 3 dimensions, okay? On occasion, I might talk about 4 dimensions. But if you're taking linear algebra, that's a fun course. They work in any dimension. Yeah, cool. Okay, now what are some examples of vectors? And if you've already taken physics, good for you, because you probably know what the answers are here. Force is a vector quantity. Velocity is a force, so that is an example of it. Acceleration. Okay, fill those blanks in, and let's keep going. So now let's talk about how you represent a vector. We're going to be drawing pictures next. So get ready for some pictures of like, what does a vector look like? So a directed line segment. A directed line segment is used to represent a vector. Really? Like, what do you mean? Well, here's a picture of a vector right here on your course reader and lecture notes. It has a point here labeled A, and then it has another point over here labeled B. The point B has an arrow there. Only one arrow, not both points having an arrow, just one. So it's a line segment that's directed, so it has a direction. This vector happens to be pointing where the arrow is pointing, so that's the direction. Some more vocabulary. The initial point is A. That's the initial point. That's the point that doesn't have an arrow on it. It is sometimes called the tail, aka also known as the tail. The other point, B, is known as the terminal point. And yes, I'm going to use these phrases in the future, so know which is which, otherwise you'll get really confused. And sometimes they call that the tip. So the tip is where the arrow is. Okay? Now, this vector that you're seeing here, this picture, does have a direction. It looks like it's pointing a little bit to the right and up. And magnitude is its length. And we'll talk a little bit more about this in a moment, but I just want you to get that the magnitude would be how long that vector is, how many units, the length. So now let's do some notation, and notation is important. So for example, when you do quiz 1 this Sunday and you turn in your handwritten work, I am going to be looking very carefully that you have honor the vector notation that we use in this course. And when you first start out, you may be a little bit remiss in doing it perfectly, and I'm going to be real nice. I won't take off too many points or anything. But as the semester progresses, if you continue to not honor the correct symbol language that we use, symbolic language here in math with the correct symbology, and then you might lose a few more points. So we don't want that to happen, right? So let's look at notation. So the notation for the vector above using the directed line segment notation is AB, and there's a little arrow on the top. So if I were to handwrite it, it would look like that. Note that the order matters. AB is very different from the vector BA, because BA would point in the opposite direction. Okay, the only thing that AB would have in common with the vector BA would be their lengths. That would be the same, but not the direction. Now, when you're reading your text or a quiz or your homework, they're going to denote vectors not with a little arrow on the top. They're going to use boldface. So this is an example of text right here. Lowercase letters are also very common in denoting vectors. So lowercase v, and it's in bold. So there's no arrow on the top, but that'll mean vectors. Now, it's very customary to name vectors with lowercase letters. Okay, well, what about here? You're using uppercase. Well, I'm not naming the vector there. I'm using the points, the initial and terminal points, to help me name the vector. In that case, typically points are labeled with uppercase letters. I'm just telling you the tradition, okay? Now, when you handwrite your stuff, and that's going to be you when you upload your quizzes and exams, you're going to make sure that you're not going to be able to use boldface, because I don't want to look around and see, you have to like use a thick pen or something. You'll just write the lowercase v and you'll put a little arrow on the top like this, or like this. You can do it like with a half arrow. I'll be okay with that. Either one of those I'm okay with on your exams and quizzes. And that means the vector v. Yeah,